Nuclear equations are mathematical representations used to describe the processes of radioactive decay, in which an unstable atomic nucleus transforms into a more stable one by emitting particles or energy. These equations provide a detailed account of the changes in the composition of the nucleus, specifically focusing on how the mass number and atomic number of an atom are altered during the decay process. In a nuclear equation, the mass number, which is the total number of protons and neutrons in the nucleus, and the atomic number, which is the number of protons, must balance on both sides of the equation. This balance is essential because it reflects the conservation of mass and charge during nuclear reactions. The principle of conservation of mass ensures that the total number of nucleons, protons and neutrons, remains the same before and after the reaction, while the conservation of charge ensures that the total electrical charge is unchanged. During alpha decay, an unstable nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons. This emission results in a decrease in both the mass number and the atomic number of the original nucleus. Specifically, the mass number decreases by 4, since the alpha particle has a mass number of 4, and the atomic number decreases by 2, as 2 protons are lost. This reduction in atomic number means the original element transforms into a new element that is positioned 2 places earlier in the periodic table. The emission of the alpha particle decreases the charge of the nucleus because it loses positively charged protons, and it decreases the mass of the nucleus because it loses nucleons. In contrast, during beta decay, a neutron in the nucleus is converted into a proton, with the emission of a beta particle, which is a high-speed electron. The mass number remains unchanged because a neutron, which is neutral, is simply replaced by a proton, which is positively charged, keeping the total number of nucleons the same. However, the atomic number increases by 1, because the newly formed proton adds a positive charge to the nucleus. This increase in charge results in the transformation of the element into a new element that is 1 place later in the periodic table. Essentially, beta decay increases the charge of the nucleus without affecting its mass. Gamma decay differs from both alpha and beta decay in that it does not involve the emission of particles from the nucleus but rather the release of energy in the form of gamma rays, which are high-energy electromagnetic waves. Gamma rays are typically emitted after the nucleus has undergone alpha or beta decay, as the nucleus sheds excess energy to reach a more stable state. Since gamma rays are pure energy and do not carry mass or charge, their emission does not alter either the mass number or the atomic number of the nucleus. Therefore, gamma decay leaves the charge and mass of the nucleus unchanged, though it reduces the energy state of the nucleus. In summary, nuclear equations illustrate the transformations that occur during radioactive decay, adhering to the principles of conservation of mass and charge. Alpha decay decreases both the mass and charge of the nucleus, beta decay increases the charge while maintaining the same mass, and gamma decay, while releasing energy, does not change the charge or mass of the nucleus.